Professor Courtney Young is graduated on 3 premier mineral and coal processing and extractive metallurgy institutions, having obtained his BS in mineral processing engineering from Montana Tech in 1984, MS in mining and in minerals engineering from Virginia Tech in 1988, and his Ph.D. in metallurgical engineering from Utah in 1994. He joined the faculty at Montana Tech in 1993, and his specialties in mineral processing and extractive metallurgy include mineral analysis and characterization, flotation, physical separation, leaching, cyanide analysis and characterization, uranium and base minerals, metal processing and adsorption. He enjoys working on recovering critical materials from primary and secondary research and is known for his contributions on rare earth mineral flotation. In this regard, most of his research is industrial related and often done through the Center of Advanced Materials Processing, CEAMP, at Montana Tech. Courtney, again, thank you so much for taking the time, for coming to Brazil, and please, the stage is all yours.
Thank you, Andre, for the introduction. Bom dia? Is that right? I pronounced okay? Good. Yeah, it's a pleasure to be here. It's been a long journey from Butte, Montana. I was in Phoenix, Arizona for the SME annual meeting that the United States has, and now I am here. And so I look forward to giving you this presentation. I'd like to acknowledge my co-authors, Trinan Bayless, he is my postdoctorate. Abdul Mahmoudou, he's my master's student on this project. And of course, I'm from Montana Tech in Butte, Montana. Starting off with the acknowledgements. I come from the Department of Metallurgical and Materials Engineering. I would not be who I am if it wasn't for them or Montana Tech. This research is conducted by the Army Research Lab, also known as ARL. Without their funding, of course, I would not be here today either. And just some quick references over the last couple of years, the last 5 publications on this, including 3 master's theses. So the outline of my talk, I'll go through some abbreviations, introduction, procedures, results. I'll have some discussions, and at any time, if anybody wants to ask a question, feel free. And then the conclusions. So the abbreviations that I have are rare earth minerals, REMs, and then REOs for rare earth oxides, and RECs for carbonates, REPs for phosphates. I don't have a lot of conversation on phosphates for this conference, but at least I have a few. And then rare earth silicates. Earth elements, light, mid, and heavy, so you can get LREEs, HREEs, and MREEs. And then the collector that we're using for this flotation study is salicyl hydroxamic acid, also known as SHA. And 2 important numbers that are going to come up in this is one that's called lanthanide contraction. I'll demonstrate this to you. And the coordination number, and I will also demonstrate this to you. It makes rare earth flotation chemistry very difficult to understand. And once you know what you're doing, we can solve these problems. So rare earth elements are not as rare as their name suggests. Here's a table of abundance versus atomic number. And if you look at the rare earth elements on there, or I should say the base metals on there circled in blue, that's copper, nickel, zinc, cobalt, and lead. But if you look at the ones circled in red, those are the rare earth elements. And in popularity, I think I said that backwards, I'm sorry. In red is the base metals, and then in blue is the rare earth. But you can see the circles are almost as high up on the y-axis as everything else. So they're fairly abundant. It's just that they're so spread out. Okay. There are a group of 17 elements that include the 15 lanthanides, as well as yttrium and scandium. And you can see these in yellow from the periodic table. They may be categorized as light, mid, and heavy, as I said before. And the light rare earths are the first 5, the middle rare earths are the next 5, and the heavy rare earths are the last 5. They possess unique property where the atomic cationic diameter decreases with increase in atomic number. That, of course, is lanthanide contraction. And lanthanide contraction depends on how it is bonded to other mineral elements, or phosphates, or silicates, or what have you. And then you can have lanthanide contraction, or cyanide, coordination number of 6 to 10. Okay? And when you are coordination number of 10, lanthanide has an atomic diameter of 2.8 angstroms, and lutetium has 2.46 angstroms. Those numbers change with coordination number. They're deemed critical materials because their supply is at risk. All countries depend on it. We have cell phones, and they're used in our cell phones. And Montana Tech is involved in a lot of research in mineral processing, hydrometallurgy, pyrometallurgy, and recycling. And I'm going to give you a talk tomorrow that involves a little bit of the recycling side of things. So this is just a list of the rare earth elements along with their uses. You can't read that, and I'm not going to take the time to read it to you. We'd be here for a couple of minutes. Any case, for those who do not know flotation, you have a vessel which you highly agitate. Anybody not familiar with flotation? Everybody knows it? No flotation. All right. Okay. All right. I don't need to describe it to you then. All right. It's practiced in China for various REM ores, and it's often with other processes. These are the mines that are in China or near China. Most of our world supply comes from this area, from these 3 areas. It's being examined at Montana Tech, like I said, and we're looking at Bear Lodge property in Wyoming, which is a state next to Montana, Mountain Pass, California, and the Conveyor Belt deposit in Greenland, and a number of others, but those are the 3 right up front. Most often found as the carbonates, phosphates, and silicates, and they can exist as oxides. Some examples are bastnasite, which is a carbonate, and parasite. A phosphate are xenotime and monazite. And silicates are allanite, a very difficult to float mineral, and gadolinite. And then their REOs are laperite and knapite. And as a result, likely to yield different metallurgical performances, whether it's flotation or leaching or what have you, because these types of minerals have different coordination numbers, and they also have different lanthanide contraction numbers. And you're going to see that here shortly. Okay, this is the flotation chemical that we looked at, and I want to call your attention to the 2.42 angstrom distance between the 2 oxygens. That is what we call the claw, and if you have an element that'll fit right into that claw, then odds are that it will float easily. Okay, and if it doesn't fit very well, then it will not float very well. Okay. It's a novel collector that can be that can deprotonate at high pH and then become an anionic collector with a charge, of course, of -1. Okay. And we use this material from ASAR Scientific, or Alpha ASAR. Synthetics, we had to make our own rare earth silicates. And the point of all this is we were using chemicals that either we made or right out of the bottle, and so that we could control the type of rare earth element that we had. So if it was yttrium phosphate, we purchased yttrium phosphate and treated it like its own our own mineral. Okay, so we can control the purity. So if you go back to those previous, like allanite, it was a mixture of different rare earth elements. Okay, so we wanted to just have a single rare earth element in these studies. So the studies that we did were pretty simple. We just did some adsorption studies and monitored the adsorption as a function of time, and whichever one gave us the greatest maximum adsorption density, gamma max, then that one obviously would float the best. And the ones that did not adsorb very strongly, they would not float very well. So that was just our procedure for measuring concentrations before and after each test, and then we could calculate the adsorption densities. Okay, we studied lanthanum oxide and hydroxide, because once you put it in water, it'll hydrolyze. And this would be an example of adsorption as a function of time. And then we could translate that into adsorption density, and this would be its adsorption densities as a function of time. Now the yellow line at the bottom, the horizontal line, that is as if you had a horizontal adsorption layer of the Sha on the surface, and the dark blue line is a Langmuir-Blodgett, and that would be like all of the adsorbed molecules are vertically oriented. So then we would compare lanthanum to oxide to phosphate to carbonate, and you can see that you're getting different numbers here. And you would not expect that, because this is an anionic collector and it's adsorbing onto lanthanum. But its coordination number affects things. Its atomic size affects things. And so we just got done studying these two types of silicates, and we're also seeing differences with the silicates themselves. So in essence, REOs and REs silicates, RE2 silicates, so that would be the one on the bottom right, and RE phosphates are adsorbing just a little bit less, and then RE carbonates and the silicate on the far bottom left don't adsorb very well either. So just remember that order, because that's for lanthanum. And then when you change up to dysprosium, the order changes. And you're scratching your head, why is it doing this? And in this case, the phosphates tend to adsorb the best. Okay? And then when you study the oxides, you get different results, even, or I should say the silicates, you get even different results. So I'll remind you again of the light rare earth oxides, the middle rare earth phosphates, and, and the heavy rare earth carbonates. Those seem to be the ones that adsorb the strongest. Okay? And anything else that's not circled on there don't adsorb as well. So to put all this into a plot, this is a very busy plot, but if you take a look at the size, the atomic diameter size on the left, and the element number is your x-axis, and you can see now that on the top line you have the carbonates, and you can have a maximum size for lanthanum of the 2.8 that I pointed out before. Coordination number for carbonates does not change. It goes all the way down to 10, or it stays at 10, But when you get to lithium, it has that atomic diameter distance of about 2.48 angstroms. Okay. But you switch to phosphates, and the diameters get smaller, and the coordination numbers become 9 and 8 respectively. Okay. And then if you switch to oxides, the coordinations number are 7 and 6, and the diameters get even smaller. So if you take a look at Sha in the yellow banded color region, it's 2.42 angstroms, and we estimate plus or minus 0.1 angstroms at the size that it would work best at. It'll capture most of the phosphates when you float them. Okay. But the heavy rare earth oxides in the bottom right-hand corner in blue, no, doesn't float. Top left, in the green, the light rare earth carbonates does not float very well. Okay, and I'll come back to this plot in a second. Okay, so, oops, we're already there. So here we are with the silicates, and as I said before in the previous slides, that they float the same way as the rare earth carbonates. The RE 4.67 type rare earths, silicates, okay? And then the bottom right, the oxides tend to float like the rare earth 2 silicates, okay? And what people don't understand is that they go, oh, you can't float those silicates very well, because we don't understand that you have different types of silicates, they're going to float differently. And allanite, for example, floats like carbonate. It's the most difficult rare earth carbonate or rare earth silicate to float. So what happens? You need a different collector. And what a lot of people are doing is they're going to dual collector systems, and they're crossing their fingers and hoping that it works. So the results help explain why rare earth silicate flotation is so darn difficult. They suggest more than one collector is needed to float rare earth carbonates and oxides. The question is, are the collector blends used? And of course, we know the answer to that at Mountain Pass, Oregon, the answer is yes. So they use a collector like Shaw, but then they also use another collector. It's a proprietary blend, but I believe it's a fatty acid and a hydroxamate. They will not tell me what they use. And by an oboe process, they use, this is a schematic on the left there, is how they do their process. But they use naphthyl hydroxamate, and in their cleaners they use phthalic acid, benzoic acid. So they are using collector blends, and they don't know why. And what you just heard today is a reason why they use collector blends. Okay. So in conclusion, Shaw adsorption was examined on several rare earth minerals using pure chemical powders of oxides, phosphates, and carbonates, as well as synthesized silicates. Results were found to vary and be attributed to the coordination number and lanthanide contraction. Ionic diameter as it relates to Shaw head group size and its chelating property appears to be the overriding factor. So that's that 2.42 claw size that needs to fit the size of the rare earth element in order to do flotation. Maximum absorption was seen with oxides and phosphates, but should also occur with the heavy rare earth carbonates. Maximum absorption for rare earth silicates, however, depends on the type of silicate. Is it 4.67 like you see there, or is it RE2, Si2O7? Results explain why rare earth silicates can be difficult to float, and results also explain why industry now uses collector blends, which is believed to be unknowingly overcome the effects of changes in rare earth mineral types and regarding their rare earth element content, non-stoichiometry, as well as purity. So future work, we're going to determine the effect of on other rare earth silicates. There's obviously more than the ones that we've looked at. Examine other collectors. Develop novel collectors. We're going to use some software to help us design some new ones and hopefully make new ones. It's easier said than done. Study favorable collectors as blends. Test various ores and deposits. Continue to look at the Bear Lodge property, the Mountain Pass property, and the Kemvenfeld deposit in Greenland. And of course, many others that I haven't even mentioned. So, for those of you who don't know American football, I love soccer, by the way. This is my wife in the yellow, and my two daughters, Jamie and Jessica. Jamie's on the right, and Jessica's to her left, or to her right. So, but I thank you very much. Obrigado.
Nós temos tempo para uma ou duas perguntas, se alguém gostar. Laurindo, cadê? Mônica? Aqui, professor Laurindo, por favor, Mônica. Laurindo, levanta sua mão um minutinho. Aí, ó, o microfone já está chegando aí.
Laurindo Leal Filho, Universidade de São Paulo. I'd like to congratulate you for this excellent presentation. I'd like to make a single question regarding the crystal chemistry of the silicate approached by your research. Because I suppose framework, chain, it's orthosilicates. What kind of silicates? Of silicate, yeah.
Yeah, we had to make them ourselves. And so we used a pyrometallurgical approach where we added chemicals, brought them up to temperature, let it melt, and let them cool. And then we broke them into a powder. And so once we had these made, we had to run X-ray diffraction to make sure that we knew which one it was. And every time that we had a certain recipe, it came out to be the 4.67, or it came out to be the 2. And allanite, if I remember correctly, is a 4.67, but it has different types of rare earths inside its crystal structure. And for these studies, we wanted to study only one rare earth element at a time. So we made a number of different silicates with only one rare earth element in that particular crystal structure.
All right, very complex, but I wish you good luck to this research.
Yeah, thank you. It's
thank
helped. We've got a lot of interest in this now, and obviously Andrea and I are going to be trying to do some studies together ourselves. So.
Thank you. Thank you.
Another, Monica, Filipov, please. Thank you very much for this excellent presentation. I have several questions, but I will ask on the conformation between collector and metallic cations. Did you see the cation density on cleavage plane? Because I agree, for halation you need have some conformation between Cu and ionic radii of cations. But what about the distance between two cations to control the conformation, your conformation theory?
Well, let me see if I'm going to answer your question correctly first. The adsorption isotherms, and you saw the two horizontal lines going across the bottom, some were well above that, and those you would think would be surface precipitation of the collector. But those that were close to the two lines would be no better than a monolayer of self-assembled, if you will. The distance between the two, which is why we calculated the horizontal, if it laid down and just kind of spun around, that would be the area that molecule would accompany. But if it would be vertical, it would be a little bit tighter orientation. And that would be similar to the Langmuir-Blodgett type.
Because this kind of analysis, in my opinion, can help maybe regroup. You regroup it only based on the ionic radium, but if you calculate cation density on the cleavage plane, maybe this will add additional dimension.
And we did do that. The reference early on with Freddie Syme, and that's a very good question because I don't remember any of the numbers, but the spacing between the rare earth sites that was going to help determine whether it's vertically or horizontally. You're absolutely right. Yes.
Yeah. Just I will complete your presentation this afternoon. I did some very small study on this on calcium mineral. Thank you very much.
That's a really good point because we did do that. I should have put that at least one slide in here on that, but thank you. Yeah.
Thank you, Filipov. Agradecemos novamente ao professor Courtney Young for the presentation. Courtney, thank you so much.